Okay, it's that time. In this lecture, we'll talk about Shor's algorithm for factoring integers. So, for the purpose of making things understandable within the scope of this course, I've simplified this algorithm in a few places. But I should assure you that even with this simplified version, all the essential features of the algorithm are present. So in other words, even after you look at all the elements of the quantum factoring algorithm, there's still an element of magic to it. Now, this element of magic is not because I haven't presented to you what's going on. Even if I showed you all the missing, the pieces that I'm suppressing, there'd still be this exactly the same element of magic to it. Okay, so let's get started. The main building block of the factoring algorithm is period finding. So what's period finding? So we are given as input a periodic function, f. So f maps the numbers 0 through m-1 to some set S. And f is periodic with period r. So what do I mean by this? Well, here's a periodic function whose period is 1, 2, 3, 4, 5. So if you look at this function, let me just draw these lines to highlight the shape. This might help you see why this actually looks like a periodic function. So out here, if you imagine this is what the shape would have looked like, and then you have just repetitions of this period. So what's the period here? So r equal to 5. And how many repetitions of the period are there? So think of m as 100. So the number of repetitions of this period is m divided by r, which is 20. Okay, now there's one other thing I should say about this function, which is if you look at it on a single period, then f is 1 to 1. So you never repeat values. So let's label the y-axis. It's 0, 1, 2, 3, 4. Okay, so what are the values of f on a period? It's 2, 0, 4, 1, 6, right? So no repetitions. And so this is an essential condition for period finding. So our first condition is f is 1 to 1 on each period. And then we'll have a second condition, which is a simplifying condition. This is one of the things that I talked about where we simplify things. So I'm going to assume that r divides m. Okay, so to actually make the factoring algorithm work, the condition under which we would need to solve period finding is where r does not divide m, but on the other hand, you get to see many, the function. You get to see the function over many periods. So you might think of the condition that m over r is much larger than r. Or in other words, m is larger than r squared. Actually, you can make period finding work with m, say, equal to 2r squared. So if as long as m over the number of periods you see are somewhat larger than the period itself. Okay, so now let's address one more issue, which is how is this function given to us? Well, here's how it's given. You're given a circuit C sub f, which takes as input x and outputs f of x. It's a classical circuit. Okay, so now how hard is it to solve period finding? So let's look at parameters. Let's assume that capital M is large. So capital M, let's think of it as a 1,000 digit number. So M is about 10 to the 1,000. Okay, how big is R? Well, we said R is about square root of M. So R would be, let's say, a 500 digit number. So it's still a huge number. So now, if somebody gave you such a circuit and said, find me the period, what could you do? Well, classically, all you could do is pick inputs, maybe random inputs, until you've figured out the pattern. But what pattern is there to figure out? Well, until you see a collision, until you see two different numbers, x and y, such that f of x equal to f of y, you're really getting no information about the period. Because the values of the function have no particular pattern to them other than the fact that they eventually repeat. But how long does it take before you get to see a collision? Well, this is where the birthday paradox sort of might come into play. It might be that, well, as you're picking, certainly you might think you need as many random inputs as R before you see a collision. But actually it turns out square root R inputs suffice to see a collision. Okay, so this is called the birthday paradox. But square root R is still a very large number. Square root R is a 250-digit number. So it's about 10 raised to the power 250. This is too large for us. It's impossible for us to find the collision classically. Okay, so what does the quantum algorithm do? Well, the first thing the quantum algorithm does is it converts the circuit into a quantum circuit. So now it takes as input x, zeros, and it outputs x, f of x. But of course it can do this also in superposition. So here's the idea. What we are going to do is we are going to set up the uniform superposition on the x's and then run the circuit. So we'll get as output summation x equal to 0 to m minus 1. Let's normalize 1 over square root m x f of x. Okay, so now what else do we want to do? Well, now what we plan to do is take this output and measure this second register. So if we were to measure this, what would we see? Well, we'd see some random value in the image. So we'd see f of a for some a. Okay. So let's say we happen to see f of a equal to 4. Okay, but there are many different values of x which give f of x equal to 4. There's 2, 7, 12, so on up to 97. The property of these numbers 2, 7, etc. is that they're exactly 5 apart from each other. It's an arithmetic progression which is 5 apart. 5 is exactly the period of this function. Okay, so what do we see here? Well, let's draw a little graph. So here's x, here's alpha sub x, right? So we measure and we see summation alpha sub x, x. And what's alpha sub x? Well, it's 0, 0, and then this is non-zero for 2, and then we just stay at 0 all the way down until we get to 7, and then we see the same amplitude, 0 until we get up to 12, and we see the same amplitude, and this just keeps going on this way, periodic, until we get up to 97, and we see that same amplitude. Okay. So now what do we do with this? I mean, why does this superposition help us? Well, there's one more trick we have in our toolbox, which is what we could do is we could do Fourier sampling. And what are the properties of Fourier sampling? Well, here's one. Remember that if we were to shift the input superposition, the output of Fourier sampling does not change. So we could shift this periodic superposition so that we shift it back so that our first non-zero is not at 2 but it's at 0. And now what happens to the rest? Well, this shifts back to 5, that shifts back to 10, this shifts back to 95. Okay, so why is that good? Because now we have a periodic superposition where the non-zero amplitudes are exactly the multiples of the period. Okay, so we have a superposition. Let me write it, so R equal to 5, M equal to 10, 100. And what's our superposition? It's a superposition J going from 0 to M over R minus 1 of J times R. How many such non-zeros do we have? We have M over R of them, so the amplitude should be square root R over M. Sorry, so this is, what we're saying is Fourier sampling this would give us exactly the same answer as Fourier sampling that. But now what is the result of the Fourier sampling? Well, the result is what we see is in fact the output that we see is a random multiple of M over R. So in our case, what's M over R? M over R is 20. So what we get to see is a random multiple of 20. So for example, the first time we might see, we run this experiment, we might see, so our output might look like 60. Then we rerun the experiment, and maybe our output looks like 80. What do we make of this? How do we figure out 5 from these outputs 60, 80? Well, what we say is, well, 60 is a multiple of M over R, which was 20. 80 is a multiple of M over R, which was 20. How do we figure out M over R from this? Well, we know it's a common divisor of 60 and 80. Let's figure out the largest common divisor, the greatest common divisor, using Euclid's algorithm that you learned in high school. Well, so the GCD, the greatest common divisor of 60 and 80, is equal to 20. So you figured out what M over R is. And now how do you figure out R? Well, you just take 100 divided by M over R, and you get back 5, which is R. Okay, so that's the outline of how we solve period finding. Okay, but how do we actually implement it? Well, here's the quantum circuit for implementing period finding. So looks very much like the quantum circuit for Simon's algorithm. So you start with, you start with your inputs all zeros. You first do a quantum Fourier transform sub m. What does this give you? So you know that if you start with the state 0, then QFT sub m gives you an equal superposition over all the, it gives you 1 over square root m, sum over all x going from 0 to m minus 1 of x. So that's what you get over here. Now you apply u sub f. So what you get here? Well, you get 1 over square root m, sum x going from 0 to m minus 1 of x, f of x. And now it turns out you can either measure or not measure. Now what you go ahead and do is measure this. Okay, when you measure this, you see f of a. And then what do? Well, we do Fourier sampling on the first register. In the circuit that I drew out before, I had not put in this measurement on the second register, and it turns out that you can either do this measurement or not do the measurement. The result is always the same. Maybe at some point we'll talk about this further, but it's something called the principle of deferred measurement. It basically, as long as there's no further communication between these qubits, it doesn't matter. It doesn't matter whether you measure these lower qubits or not. You'll get the same answer on the upper register. But in any case, what you do now, okay, so but conceptually it actually helps to think of doing the measurement on the lower qubits. So we measure them, we see f of a. And so now we have got this periodic superposition out here on these qubits. Now we do another quantum Fourier transform and then measure. So this is Fourier sampling. And this Fourier sampling, what we know about Fourier sampling is that it has these two properties. One, that shifting the input doesn't change the output distribution. So we may as well shift it and think of the output that we got here of the measurement as f of 0. So now our shifted superposition is 0, r, 2r, etc. When we do the quantum Fourier sampling, we'll get a random multiple of m over r. And then we repeat this circuit a few times, collect samples, compute the GCD. The GCD is m over r, and that gives us the period r. Okay, to complete this story, let me just tell you what happens if we do not make this simplifying assumption that r divides m. So in this case, what we'll assume is that m is large enough, say it's larger than 2r squared. Another way of saying this is that m over r is at least 2 times r, meaning that the number of periods that we look at is comparable to and larger than the period itself. Okay, so in this case, the quantum circuit remains exactly the same. So we follow the quantum circuit, we do as Fourier sampling. The output, let's say, is some number L. So now the claim is that L over m is approximately equal to some t over r for some number t, some integer t. You know, of course, if you were to rearrange it, this would tell you is that L is some multiple of is t times m over r, the sort of thing that we were saying in the simplified scenario. Okay, but now what do we get out of this? So it turns out that there's this beautiful way of, so what do we know here? Well, this was the output of the algorithm. M we know. This we'd like to know. And this is, t is just an unknown, so we don't know it. So how do we figure out both t and r, or at least r from given L and m? Well, it turns out that what's used, and this is sort of too advanced for this course, is that t over r is the best approximation to L over m with a denominator as small as r. So we use the fact that r is much, much smaller than m. It's smaller than square root of m. And so you can show that t over r is the best such approximation that you can get to the fraction L over m, where the denominator is smaller than square root of m, square root of capital M. And given that, you can actually reconstruct t over r using a technique called continued fractions. And you can actually do this, you can recover these numbers very efficiently, very quickly on a classical computer. And so you can solve the period finding problem even in the case where r does not divide m.